Okay, now we will continue with the programming and software structures, so programming language structures in general. Now we mostly focus on solving a problem by using computers. We have seen it. Okay, so we have seen the developments in computer technology, in fact, and now the point is there should be some interface between us, between a human and the computer. So that is software. Basically, computer understands only the numbers, and we will see how the numbers are evaluated in a computer. But the point is, we are engineers and we want to solve an engineering problem by using computers. So how we do it? That is the question. So we need to understand how we solve a problem in general. Okay, so first thing is, before the computers, what we did was, first we put the fundamental physical laws of a problem. And in order to put these physical laws, we use mathematics. Before 15th century, it was numbers, because heavily depends on the things that we deal, heavily depends on the numbers. We wanted to build things, and therefore we need to calculate the areas, volumes, and so on, or masses. We want to measure the mass and say something about the object. And therefore, until 15th century, it was the numbers. And as the calculus get into the science, more get into the science, now we begin to use the functions. So continuous infinite number of points. As a result, we are talking about infinite number of numbers. So the rational numbers get into the play. Then we begin to talk about the functions and operations by using functions. We want to we begin to define the things by doing operations on the functions. And certainly we want to solve some more complicated problems. Now we have infinite number of points, therefore we have infinite number of numbers. And then what we did was simply we begin to define the response of an object or response of a thing within an interval. So this mathematical operations are can be named as fundamental laws. For example, second law of motion, first law of motion, or Hooke's law, for example, the relationship between the material or reaction of a material to a force. Okay, then we solve it. So we do some operations on it. We obtain some function or some numbers, some value, and then we try to make a comment what it means, what the result means. This is the thing that we did before the computer era. Okay, now how about the advent of the computers? Sorry for that. Okay, that's better. Maybe you don't need to see me anymore, my ugly face. So the point is, more or less, the advent of the computers, invention of the computers changed the things a little bit, but little bit, not so many, not too much. So what the case is now, again we need a formulation. So we need to define the thing with a mathematical by using a mathematical expression. So that is the first step in solving a problem by using a computer. How about the next step? Now, next step is to use the computer to solve this problem. Now, the computers can solve a problem in a discrete manner. Even though we think that it's continuous, it's not continuous. We will see in detail. And certainly, since the computers are capable of doing much more faster calculations than human, because they are machines. So computers are simply a machines, and they do only things whatever you want them to do, or whatever you teach them to do. So simply. And of course the last step is the same. So interpretation. In fact, again, you get a result, you get a discrete result, but you have now too many points. Of course, too many points means that there are finite number of points. It's not infinite, but it is too much. It is there are so many points. Therefore, even if it is discrete, it gives an impression of continuous. It gives an impression of a continuous function. Okay, so what is the advantage of using computers? We can do many operations on it. So you can do 2 billion operations in a second. In fact, this is not a human can do. And moreover, you can solve much more complicated problems because it is faster, and we will see how it is done by using the computers. Okay, so we use a mathematical model. The first step is to find the proper mathematical model for our problem. So what's a mathematical model? We all know functions. So functions defines a thing, infinite number of points, as we said. Of course, there are certain things which are related with the functions. First of all, the outcome of the function is called dependent variable. Okay, so this is the dependent variable. And what else we have? We have independent variables. We have parameters. And we have forcing functions. So what are these? First of all, independent variables. So we are living in a three-dimensional world. Of course, so therefore, in order to define a place of an object, we define generally 3 coordinates related with this object. If you are sitting in the corner of a room, you say that, okay, that object is 3 tiles in front of me and 5 tiles on my left side. And it is 5 tiles above the ground. Now I define the position of an object in the room relative to me, relative to my position. So that means that I am at the origin of my definition. So certainly this means that the position, these number of tiles or the coordinates, in other words, are independent variables. If the object is moving, then there is another parameter get into the play, and that is the time. So okay, I say that at time equal to 0, at the beginning of the event, the object is somewhere here, and then as the time passes, it moves. So what is the time? The time is, according to the Einstein, the ticks of the clock. So 5 ticks, after 5 ticks of the clock, so the object moves to here. So again, time is an independent variable because it doesn't depend on any other thing. So this is what the independent variable is according to mathematics. Okay, how about the parameters? Now we have different things. So I measure the velocity of the object. So what is the velocity of an object? Basically, it is the change in position within a unit time. So I measure the distance that it travels, then I divide it with the time, and I obtain the velocity of the object. That's okay. Now velocity is a three-dimensional, it's a vector quantity, right? It has a magnitude and direction. So you may have different directions for the same magnitude. It is different than the speed. We have seen it. Now a parameter. Now consider that you have the two vehicles, okay, moving on a road. So let's define it like this. Now you have one road and a car is moving on this road, okay, and just think that there is another car and there is another road which is parallel to the first one. Now the point is this: just imagine that they are moving with the same speed. These are my cars and they are moving with the same speed. Now remember that the velocity is the change in position per unit time, in unit time. Of course, these two cars are moving in the same direction with the same speed, but in fact these two cars are different. And what happens is this: there is a distance between these two roads. As a result, the distance between the roads is a parameter. You see? So this is the distance, the red line. Okay. Now this is what the parameter is. This parameter is constant, which gives me the, if I want to define the, for example, some quantity about these two cars. Now there is a parameter between, if I want the, between the function that I define the motion of this car and the motion of the first car. Okay, so this is what the parameters are. So this is one parameter, the distance between two roads. What else? We have the forcing functions. Now what's the forcing function? Now I'm measuring the velocity. I'm just still speaking about the velocities of these two cars. Now just imagine that. Let's focus on only one of the motion of one of the cars. Now just imagine that there is a wind blowing in a certain direction. Okay? Certainly this wind speed will affect the motion of this car, these two cars, and will try to drive them out of the road. And that's the forcing function. And as a result, the motion of the car, for example, the velocity of the car, of a car, depends on the position and time, distance between the roads, and the forcing functions, for example, the wind speed. So this is how we define a mathematical model. So basically we have independent variables, dependent variables, parameters, and forcing functions. Okay, so let's return back to our problem solution. How we solve a problem in a computer. Now, first step is the problem definition. Okay, so what's our problem? So basically we have a car, and this car moves from one point to the other. Okay, so it moves from here, from green point to the red point. This is our problem definition. And now we want to solve this problem. So how it travels from green point to the red point, we need a mathematical model. For that, first thing that we need is the theory. We need a theory for this, which defines the physics in a mathematical manner. So we use a theory. For example, second law of motion. Second law of motion tells us that force is equal to mass time acceleration, or mass time change in velocity. Okay, now we need to solve it. So what else we need? We need the data. What's its initial position? How it moves from one point to the other. So what is the power of the engine? What is the friction between the tires and the road, and so on. So we need the external data. Then next step is the problem solving. We gather the theory with the data and we put it into the computer. So problem solving tools. So let's look at them: computers, statistics, numerical methods, graphics, and so on. So you may use different approaches depending on your problem. Generally, many of the problems that we deal are deterministic problems, and certainly this means that you can directly use computers and numerical methods in general together along with the graphics, but sometimes statistics can be used because it's very difficult. It may be very difficult to find some physical laws for certain type of problems. Then what you do is you do many measurements as much as you can, and then you look at your case and you try to find out where your measurement is in the statistical distribution, and you try to make a comment on it, define the outcome of the thing. So this is how the statistics works. Okay, then you do numerics. You obtain the numerical value or graphic, or in general, let's say the results. You obtain the result, and the last thing is you share it with some other people. Of course, what you do is, if you, for example, you just make a simulation and you determine the stress distribution in a bracket, and you share it with the designer, and you tell the designer that, okay, there is a point where the stress is much higher than the strength of the material. So modify your design, or you share it with the manufacturing engineer, and you say that, okay, be careful about this point. This point is highly susceptible to the manufacturing method. So choose the proper manufacturing point according to this. So then it goes. Okay. Then, of course, what you do is you do the job. Okay, what type of problems that we see? For example, we may have a bunch of reactors in a chemical process. So you do like what? Just let me think. We do not use reactors very often, but let's say the paper industry. So basically you try to obtain the cellulose from some biological material, biomass, let's say, specifically the plant and their residues, and then you put some chemicals, you try to remove some of the chemicals in one step, and then you take it outside and you put it in another vessel, and certainly you may need to stir it, you may need to heat it in order to initiate the chemical reaction, and then okay, there is another process, for example, which you prepare suspension or solution, and then you combine the outcome of these two processes and obtain the product. Okay, so this is the problem that we want to solve. We need to predict the mass flow rate or the reaction rates or whatever it is. Then what is the mathematical tool if you want to design such kind of a system? Of course, the conservation of mass, because the mass gets into the system has to be equal to the mass get out of the system because of the conservation of mass. Otherwise, you need a very, very big or infinitely growing vessel. So this is our mathematical model. Then we write the mass balance for each reactor, and then we solve it. So change of mass is equal to input mass flow rate which get into the reactor minus mass flow rate which get out of the reactor. What else? Okay, this is a thing that we are familiar with. Basically, we have a truss system here which is fixed to the anchors, fixed to the wall with anchors, okay, and there exists an external force. Now in this case, conservation of momentum or conservation of mass is applied, because we know that at each junction sum of the forces has to be equal to 0 for static equilibrium. So this means that sum of the horizontal forces has to be equal 0, and sum of the vertical forces has to be equal to 0 for this configuration. Now we obtain the mathematical model and we define our problem, we find the theory for this, and then we devise a mathematical model for our problem, mathematical expression, and then we solve it. So this is what we do in a computer. And then we say something. Okay, now we have the mathematical model, but we have to put it into a computer. That's fine. How we do it? Now we know that every computer has a screen and a keyboard. This basically means that we input something and we see something. We input something to the computer and we see something from a computer. Okay. Now and as we communicate with each other, we need a language in order to communicate with the computers. So therefore we have some tools, some softwares. First thing is, okay, we need a language. What are those languages? There are different languages, as is the case in our world. So we speak English, we speak Arabic, Turkish, Spanish, Hebrew, or whatever it is. Many languages, Latin. So also there are too many languages in on the computer side. So first thing is, for example, COBOL is one of those. This is a very old computer language. I mean, this is more or less an historical order of the development of the computer language. Then Fortran, formula translating language, that is the one of the first programming languages which we used, and still it is quite popular and widely used for scientific computing, for example, in engineering community also. So how about the other? Basic. Many of you knows the Visual Basic, because Visual Basic gives some nice tools, so nice looking tools, generally used to develop some interface between an engine, and I will talk about the engine. So what I mean by the engine, it is not an engine that we have in a car or in some other machines. So basically engine is something else. But BASIC is in another programming language. There is Pascal, C, and very recently Python maybe. There are many other programming languages, but these are not very well known and mostly not used not very common. Today many of you knows C and Python maybe, and some of you maybe knows BASIC due to the Visual Basic, but Fortran is also very good and strong. So what does these computers programming languages do is important for us. So that is the interface between us and computers. What they do is they convert the commands, they convert the our words, let's say, to a thing which can be understood by the computer. And normally these are the translators. Okay, so still we are not directly communicating with the computer. So these are, you can even think like that these programming languages are just the translators, and they all translate the commands that we give to another language which is called assembler, because this is the only language that the computer knows. Okay, so this is called machine language. Assembler is called basically the machine language. Simply, we can think like this, because these languages have different commands, but assembler is very specific to the microprocessor that you are using. So every microprocessor in a computer might have different commands. For example, if you are using an Intel, it may have different assembler commands, assembly. And if you are using AMD, it may be different. If you are using a Motorola microprocessor, it may have different commands. So what these programming languages do is convert the things that you want from the computer into a microprocessor specific commands. Okay, so what else we have? Now we are engineers and we mostly want to use we use mathematics in general. So mathematics is our fundamental language. There are also mathematical packages in the last 20-25 years. So the history of the programming languages are as old as computers. So you can think like 60 years, maybe more. But mathematical packages are very recent, like 25 years or 30 years, let's say. What are the mathematical packages? There are many other mathematical packages, but these are the ones which are known widely. So MATLAB is well known and commonly used when when you are heavily when you do things heavily depends on matrix algebra. There is MATCAT. MATCAT is heavily used when you are constantly doing a similar type same operations. For example, you are constantly you are designing a project, you are making a project, and you want to design something. You constantly calculate the pretension force of a script, for example. Then you write a simple script or tool in MATCAT and it goes like this. Maple and Mathematica are packages which are widely used for symbolic operations. For example, integration of a function, derivation of a function, solution of ordinary differential equations, and so forth. Of course, each have advantages and different disadvantages, but bear in mind something. What makes the difference between the mathematical packages and programming languages is their structure, their fundamental structure. So basically, these mathematical packages are written by using one of these programming languages, but these programming languages are directly written by using assembler. So these mathematical packages first indirectly converts the commands that you do into one of these converted to the one of the programming language, and then it's converted to the assembler. Generally, these mathematical packages works much slower than the programming languages. Of course, if you are able to write a code in assembler, it is much more faster. So these are the things that we are going to learn within this course. So how we can use a computer, and what are the critical points that of the critical things that we, or not the critical, but the tricks in using a computer, let's say. Okay, let's look at the structure of a software and mathematical package, let's say. Now, two common language, at least I know Fortran and MATLAB. I also used Maple and MECH in the past, but I have never used C, for example. But doesn't matter. Now, as soon as you know how to define a variable, so I will talk about it in a moment. How to define a variable in a programming language, how to make an iteration, and how to put a conditional statement in a programming language. You can do many things. The rest are generally the details. Of course, programming is heavily an experience dependent work. So as you write more codes, you become more and more experienced. Okay, let's look at the Fortran and MATLAB. First thing is the type declarations. So what is a type declaration? So you define a variable. That's the first thing in a programming language. For example, real. So that is the real numbers. Integer. The number that you define may be integer. Then you define it. It may be a string. Maybe you want to define a text. Then you use character. Or logical. So 1 or 0. True or false. So that is the logical. So these are the fundamental, first fundamental element of a programming language. The second thing is making an iteration in a programming language. So you want to do an iteration, you want to count a number from 1 to 10, for example, and how you can do it. That is the second thing. And conditional statements. So what is the conditional statement? So it is like this. You want to tell the computer, okay, if you go up, be careful, if is the critical word here, if you go up to the second floor, this is the condition. So if you go up to the second floor, turn right. So turning right is the statement, and going to the second floor is the condition in this case. So go up to the second floor, and then if you go up to the second floor, turn right. So what might be the alternative? If you go up to the first floor, then turn left. So this is the conditional statement, and of course each programming language or programming package might have different commands. So if you want to learn programming language, these are the fundamental elements of the programming language, and these are the first thing that you should learn. For example, in Fortran it is real 4. For the 4-byte real number, we will see what a byte and what a bit is. And then real 8, 8-byte real number, integer number. And then you put the variable here. And then character. You also give the string length. Okay, how about the iterations? You say that do I is equal to 1 to n. N can be a number, any number, and possibly it is an integer. It should be integer. N has to be an integer in Fortran. Then you say 10. So do this thing. So what is then you put the command. Then what you tell to the computer is do this operation n times. So if you say here that write 1, this means that computer will write 1 10 times on the screen. Or we will see it, but you can do summation, multiplication, or whatever it is. You can do lots of things. What else? We have conditional statements. If, okay, if 10 is greater than 5, we know that it's true, so it makes an expression here. So how it works is like this. If 10 is greater than 5, this means that this condition is true. Now this is logical, and it is 1 in real. This is how the computer understands this comment. So it is like this. If x, so just think that you have a variable which is x. If x is greater than 5, then write 1 on the screen, and you close the conditional statement with the end of command. It can be different if x is smaller than this number, or you can do like this. We have seen the logical operation in mathematics. If x is greater than 5 and y is smaller than 2, then do this operation. Of course, you can combine all of these things. How about in MATLAB? Because we will heavily use MATLAB in this course. You don't need to make a type declaration in general, because numbers are automatically defined, and generally they are defined as real numbers if they are used with the points. Okay, so if you say that 2.0, it's a real number, but if you put 2, sometimes it understands it as a real and sometimes it understands it as an integer. You have to be careful about it, but generally you don't need to make a type declaration except then this strings. It's rather complicated, but we will see it in it may be, it's not, but it may be seen as a complicated issue, but we will see it in detail in the forthcoming lessons. So look, now instead of using do, now I have here I. Now here is one important thing, the syntax. Syntax is how you write the commands. Now I can write it in capital letters, or I can write it in small letters. For Fortran, doesn't matter. Also in Fortran it is the same thing, but in the old Fortran case you have to write every command in capital letters. So the Fortran differs in the capital and the small letters. Okay, so for I 1 to n, and I put double dot on it, okay, here 1 to n, then I write the command and then I close the loop. This is called loop, by the way. This is a loop and this is a loop. Okay, so I do this operation or operations n times, beginning from 1 to n. Conditional statements, it's more or less the same like the Fortran. If x is greater than something, then do this. Then close the loop, or stop the conditional statement. So this is the point, this is the command which means that the conditional statement is ended. Of course you have to obey the rules in a computer, otherwise it will make an error, it will give you an error. You all know about it. Okay, now let's